minus 2 non-dimensionalized of your x is equal to r over a.
Oh.
That's my field. And then you integrate x squared e squared dx. And when I integrated that, I got like a number. I just did it numerically. Actually, I didn't. I allowed Maple to do it numerically, and it came out with a number like 1. It wasn't 1. It was 5/4, or I can check. Let me see what did it actually come out to be. 5/4. Okay. Yeah.
When we were doing this problem for the last homework, we weren't supposed to carry through and find the actual self-energy. Is that for this one?
Yeah.
We were.
You did it last time.
Because last time I did this.
Last time, what happened was in the homework session, this homework session, I said, oh, that's a little bit more than I wanted you to do. And I sort of pulled back and said, just set it up, find the field, and show me what you do for the next stages.
If we turned it in last time, can we just use that as opposed to read to it? Because I also
Yeah.
work on it.
I mean, once you get it, when you ever get it graded, back graded, then remember this and come tell me, because she's just going to grade it straight, and then I'll make corrections. If you hand it in once, that once is good enough. Yes.
And in addition to that, you also want a plot of the derivative of that and rho.
Yes.
Thanks.
Yeah, so the electric field looks like this. And the derivative looked like that. And rho is easy. Yes. I want you to plot them. And I actually want a plot that is scaled prior. I don't want sketches. Don't do that. I want you to actually use Maple Mathematica, something, in order to actually plot it out.
So you want the field, the derivative of the field, and the charge?
Let me see what I asked for. I actually wrote it down.
Charge density.
Yeah,
the field and derivative.
Also, can you move? I can't.
Camera cannot see the board.
Straight
Not just
wire.
the camera. I can't see the board.
What?
Thank you.
Yeah, my instruction was complete Ohanian problem 5.05 by plotting rho of r, E of r, the EDR, and computing the total energy. So that was problem 25 instruction.
Can you plot it on your calculator and take pictures of it?
If you can then print it out, sure.
Yes.
No,
What?
I just changed my mind. No.
What I just did?
Oh well.
He couldn't
So-
get Mathematica to do it.
It wouldn't work.
Yes.
Well, congratulations.
So
You're
that's a
better
problem.
programmer than I am.
That's a problem for you and Mathematica to resolve together.
Brian, did you try to get Wolfram Mathematica?
Yes.
I mean, if you want to put it in Excel, go ahead.
I did.
Wolfram Mathematica.
But I strongly suggest you not do that.
What? So what's
And I should say the reason that I'm doing this, by the way, is that, so it's not my fault. Professors Meunier and Napolitano have, what are you doing?
I couldn't see
Oh, you
the
can't
bottom plot
see,
through
so-
his head.
Oh,
So I'm lifting it up over his head.
okay.
What did you say about Excel?
I say, so let me go back to the rationale. A few weeks ago, they said students are getting up to the senior level courses and they can't even make a basic plot. A computer level basic plot. because they don't know how to use Mathematica or whatever. And we need to make sure that they can.
Then ask
So
your
then
programmer to do it.
This presented a very nice opportunity for me to say, okay, now, next time around, when they say, hey, they can't do this, I could say, I assigned it. If they can't do it, it's because they refuse to learn. Or just want to take pictures of their calculators.
I can work just fine with my calculator.
Can you, does that calculator have an output? Can you plug something into it, or can
Yeah.
you do an infrared?
Not infrared, but there is cables, but I don't think me or him have the right cables.
I
So that
actually
you
think
can
I do have the right
output it and then plot it.
I have direct cable, but it's a long
It's a very basic skill.
Yeah.
Okay.
Professor,
Yes.
if we use that, had you used, as you said in class, you scaled everything, you let A equal 1 and B equal 1, right?
Yeah.
Okay, and
If I
that's
didn't bring
acceptable
my
as far as
PowerPoint.
what we need for the, okay.
Yeah.
And also, I think you already said this, but if we already computed like a value for an energy, like on a period somewhere, like we went and did it, or trying to do it, that's okay if we don't do it again or something?
Yes.
Okay.
I will, but you'll have to remind me later on.
Okay.
When, she doesn't give you the points,
Okay.
then you have to ask for the points.
Yeah.
Okay. And so I finally did the numbers and I got 4 MeV, 3.8 MeV. So it's much smaller than, I thought it was going to come out to the rest energy of the proton, and I was wrong.
Do you want us to provide a reason why it's so much smaller?
Oh, that would be great. We're not going to grade you on that.
Like, not even close.
If someone could come to class, next class, and explain to me why it's so much smaller
I really do.
to everyone else, that would be good. Okay, what next? Are we done?
The next problem, please.
Was the next one the one I made up?
Yes,
Yeah.
the wire along the Z carries.
Okay.
density lambda.
Let me tell you how I wanted you to do,
Okay.
right? I want you to write the electric field in the rest frame of the rod. I don't know whether I called it a wire or a rod or.
Wire.
Of the wire. Okay? And that's really easy. We all agreed on that?
Yeah.
Really easy. Then, actually, I'll rewrite that in a slightly, in a way that will make the transformation easier. So that electric field has a magnitude which depends upon distance, right? Which I'm gonna, it's easy. I'm gonna make you work it out. X hat plus Y hat. Normalize it. Points out radially. Okay? And then you can construct a field tensor out of this. That's going to look like, and I'm not going to get it right. I have it right there, but I'm not going to. I think it's 0, EX, EY, EZ, and it might be minus up there, EX, Y, EZ.
What changes if it is minus up there?
Nothing.
Nothing.
Okay.
Wait, it's got to be anti-symmetric.
I know, but it is minus. Yes, it is minus. That is the way O'Haney writes it, and I'm not sure if that actually is the same thing.
Nothing changes.
Awesome.
Okay. So I would have magnetic fields in here, but I don't have any magnetic field. I don't have any electric field in the Z direction. So I have zeros in there. So that's my initial tensor. Now I'm going to boost that. And the way that you do that is to multiply on both sides. It actually doesn't matter. One side is A and the other side is A transpose, the Lorentz transformation. And the Lorentz transformation is going to look something like this. Gamma 0, 0, gamma beta. That sounds good.
Alpha gamma beta.
It's negative. That's what it says.
Yes, it is negative. You're right.
What? Yes, that's what it says.
It's on the
X direction or the direction.
So when we're doing this, are we doing an inverse Lorentz transformation from the frame of the proton?
Yeah, I don't care.
Yeah,
It
okay.
actually doesn't matter which way you go. But properly, it would be the negative.
Yeah.
But you're gonna get, well, all that is actually, it's not gonna make any difference whatsoever. But then you can ask, okay, what do I expect? If my charge is moving along in this plus z direction, then I'm gonna get a magnetic field, as you remember from physics 2, that circulates. So by the time you're done, you should find that the x and y components of the magnetic field would turn out to be here, right? Are the same magnitude, and the y component points in the one of them points in the negative direction so that it circulates.
So if you use the negative sign right there, do you get the correct sign in the field tensor? Or do you then have to, okay. Switch
What
it?
you'll get is, you'll get, that's a good question. It's got to work out. Right. I think you'll just get, in the end, an overall minus sign.
Yeah, I think so.
But the relationship between the x and y components is still the same. So it turns out that no matter what, it rotates in the same direction. Yes.
Is the first matrix supposed to be transposed to the other? Oh, it's,
Yeah, but it's symmetric.
And then what? Like this is from what basis to what basis? Are we like? One's already from what frame to what frame?
Oh, okay.
Right.
Then I'm,
We're changing like according to the bases.
yeah.
So where are we?
So this was the question that that Jacob was asking,
Oh,
actually.
I'm sorry.
Which is that, so I'm sitting here and I have a chart which is observing this current, this charge here. Now I start this moving, all right? But I want to observe this thing moving in this frame. I think that's what we have to do, right? But that's the same thing as this moving in the negative direction
Okay.
relative to that. Okay? I think that the transformation that I did just here was this moving that way rather than this moving that way. You get the same numerical results, whether this is going this way or this is going that way.
So we're going from the stationary frame to the stable frame?
Yes. One way or the other, we're observing this moving. Okay? Yeah.
Quick question, I mean, you sort of answered it, I think. We get to treat the line of charges anyway, right?
Yes.
Okay,
And so that transformation matrix is well known.
What?
That the boost transformation matrix is well known.
That's, you'll actually, that's a good
You
question.
want us to
What he did was he gave us the boost transformation matrix in the textbook
okay.
for a boost in the x direction. And that looked like this. Gamma minus gamma beta, 0, 0,
Oh,
gamma, 0, 0,
so it will change.
minus gamma beta, 0, 0, 1, 1. That's the one that he gave us, and that was for the x, velocity in the x direction. Right? But then, you look at this and you say, okay, how would this change if I were moving in the z direction? Well, my velocity would move over to the z direction, okay? That's going to move there. And then you look in here and you say, well, this gamma was operating on x before. I'm going to put it on z.
But like,
And that works.
okay. So I guess what I'm wondering is, should we know where that was constructed from?
This guy.
I'm gonna try to do it.
Because I don't really want to know that.
What? Yeah. Say that because
Like, should we know where like that matrix was constructed from?
I would say it is sufficient for this class
So just kind of know that it's.
to know that that's the operation that you perform.
Okay.
Okay? And you should, I mean, you should be able to do something like say, oh, I've given the matrix for the x direction. How do I change it to make it appropriate for the z direction? So you should be able to apply some simple logic to what you're given and
You can also
change it. Right? You can also look it up, but,
or solve for it.
but it's not given in O'Haney.
Okay.
He only gives you the x. And I learned from Professor Trincala, by the way, that he actually had to borrow, I had a second one of these, he borrowed my other copy of the electrodynamics book, because the general relativity book assumes you know everything that's in here. And apparently this book also assumes that you know stuff that's over there. So what he does is he treats the two books as inseparable, and you really should be learning both of them.
Griffiths and.
No, Ohanian and Ohanian.
GR book.
Ohanian has a beautiful, it's a lovely book, but apparently doesn't explain anything about special relativity.
Oh, just like, well, where are you coming that?
So if we're moving diagonally.
So he doesn't put everything that you need here. If you're moving diagonally, yeah, then you've got a velocity in the x direction and in the y direction, and you treat the gammas for each of those directions.
Or you rotate your coordinates.
Yeah, you rotate your coordinates and slides in that direction.
Yes, I like that. Okay, yes.
Would it be possible to also solve for the tensor by trying to solve for A? How did you in the original form when you have it?
Yes.
In solving for the differential equation?
Yes.
But this is easier.
This is, yeah, this
More
is,
what we're used to.
this is more what you're used to.
Yeah, this.
Yeah. Now, unfortunately for you, next class we're gonna leave special relativity and this part behind. My main objective here was to show you where the B field, how the B field just pours out of the postulates of special relativity and the Coulomb field. And I did not do a very careful job of that, but I hope that I should have had my hands there. I hope that I waved my hands enough to show you that it could come from the postulates of special relativity and Coulomb's law, and then we just say, okay, how does it have to transform? My goodness, we get this other thing there that's the curl of one of the four vector potential. And if we give it a name B, then it turns out that it has all the properties of the magnetic field that we know. Which we just find out here. If you do the transform, what you find out is that there is a field that comes out of this. We don't have to call it a magnetic field. There is a term that once you've done your transform, you get a term here, which is like gamma beta E. And that is your magnetic field.
Yeah, okay.
Yes.
Two questions. First
Oh,
one.
and you do the same thing, by the way, for the particle in the, where the
Oh my
proton's
God.
going past the electron.
Oh, that's 8.04.
You do this?
Yeah. You can do it again.
It's supposed to be something like traveling 0.9 17 more nines the speed of light.
Yes. Yeah. It happens.
It's a cosmic ray.
Yeah.
Okay.
When you have a field tensor, what does it operate on in order to get some kind of useful information out?
Oh, so you might want to find the force on a charge.
Quite possibly.
For example. All right. Yeah, well, the field operates locally on each charge, well, you know, on each portion of the charge. So, the field tensor is going to lead to a force tensor. And the force tensor tells you the acceleration so I actually think,
How does one connive?
I'm wondering whether it's, let me hold off on answering that question and answer it tomorrow, because I haven't reviewed it.
Okay.
But I'm just going to say off the top of my head, it's like a vector multiplying a constant, you know, a scalar. Q is a scalar, for example, and force is EQ.
Okay.
So each one of those terms in the field tensor gives rise to a force in a particular direction, and that's what the force is.
Maybe just a force in four-dimensional space.
Well, we have to ask what we're going to get on the time component, and I have nothing there. So there's nothing there because I don't have time varying field at this point. I will. We will very soon have a time varying field. But for the static fields that you know, there's my 4 vector that's going to turn into a force, and the force on the particle in the x direction is QEx, QEy. I'm going to have terms over here, and it's just going to be Q times that term there, which is going to include a velocity in it. I'll get QBB, right? Yes.
No.
Yes and no. Yeah, I'm happy to talk about them. The other 2 relativity questions.
Yeah.
7 what?
12.
7, 12. Okay. Let me first say that problem 712 should be very easy. So if you're searching for a really complex thing, it's pretty straightforward. You just want the total. I have forgotten the formulas, and I didn't bother to review this one. But I seem to remember that it is just, you know, kinetic energy is equal to total energy minus mass energy. So let's see. What number was it?
7 and 12.
12. Yeah. Total energy is the same, no matter what frame. Right? So you can calculate the total energy in the frame with the particles going at very high, one of them going at a very high speed, and it's 1002 GeV. Okay. That's the total energy.
Isn't that like, shouldn't it be like 1001 because MC squared is only about 1 GeV?
Yeah, there are 2 protons.
Oh, yeah.
All right? Not that it makes a big difference here. Right. And then you take that total energy and you share it between the total. No, okay. What do we want to do? We want the center of mass frame.
Center of momentum.
Center of momentum frame. All right.
And what's the velocity of that? This is what it's asking.
Yeah.
Yeah, the center of mass frame and the center of momentum frame should be the same spot.
Yes. And I'll just say that the trick is that the total energy's got to be the same. So, or rather actually no, let me take that back. The 4 momentum is, the 4 momentum is frame independent. It's invariant, right? So, in the center of momentum frame, the momentum is 0, right? And all of the energy is in the first term, it's in the energy. I haven't thought about it. But you definitely have to use that the 4 momentum is invariant, which is E over C, P1, Px, Py, Pz. You've only got one P term to worry about.
But the total for momentum?
Total 4 momentum. Yes, for both particles. In one case, one particle's fixed, and the other one's moving.
So we have just the one form to describe both particles.
No, it's one for each. Yeah.
Do you want us to explicitly do the problem with 4 momentum?
You don't.
Because I worked it,
No, you don't have to do it for momentum.
okay.
Did he give the answer to that one?
Yes.
All right.
And you said the position of,
So I'm going to leave you to squirm on that.
and you said the position of center of mass and center of momentum frame should be the same?
Yes. Zero. Because it's infinite. Otherwise, it would be a very hard problem.
Could you just go over generally like the energy and momentum relationships for special relativity?
Yeah, I have to tell you I'm unprepared to do that, and I'll screw it up.
Yeah, I know that, but there's other stuff. There's like C is equal to gamma, or E is equal to gamma energy squared. E is equal to
Kinetic energy is mv squared.
Oh, so I am curious now. What text did you use for quantum 1, quantum 2? Okay. Oh, so you, but for so
Modern.
what text did you use for modern?
Townsend.
Townsend. Down in the library here, you'll find a modern physics book by Rolf. And Rolf is a particle physicist who was very careful about the special relativity energy scattering, did Compton scattering properly. You should be able to find all all the relationships that you need in both. Correct. Yeah. I can summarize them, and now that you ask, I will go through and collect together one page of relationships that could be useful.
Yeah, because I always get confused about that stuff. It literally gets me every time.
Okay. I'll try to put together a group. Yeah.
Does the union have a sufficient description in chapter 7 for all those relations?
Yes. Yes. I've been told that, yeah, yes. And then for the last problem, that is find the electric field in the frame of the proton and then boost it using the same
In the electron.
thing that we did here.
It's in the electrons restaurant.
Yes. So what you do first is you find the electric field in the frame of the proton. And then you say, okay, now it's going to be observed from the frame of the electron, which is traveling at 0.99999 C
17 lines.
with respect to the proton.
Okay. And you get the balance. I solved this last year. I've been through when I look how nuts that is. So how do you solve these?
Oh.
Yeah, and that's actually a real, quasi-real problem in that cosmic rays do have that energy. Some of them, very, very few of them do. And there's a whole project down in Columbia where they're just looking at the entire sky as a scintillator and looking for cosmic ray showers that originated from one high energy particle.
I know what
Does that mean you get like a time-based tensor definition
At that instant.
at that exact instant, everywhere else? It doesn't.
That's
It's
right.
kind of weird.
Yes.
Oh, but then it's just the magnitude of that.
That's it.
No, we just leave it as a tensor.
You find the magnitude of the field.
I
I think. Well, when you've made the tensor, then you look for the electric field. EX is there, EY is there. You just pick the fields out for me.
Okay.
Okay?
This thing right there.
Yes.
What if I wanted to boost along? What if I wanted to boost along more than one axis? Like if I wanted to boost the electric field, you got 45.
You need to, then you add terms.
Oh, so it's not like a portion of negative gamma beta. It's negative gamma beta, negative gamma.
No. Each gamma is for the particular direction that you're going. VX, VY, VZ.
Okay, so that's where
It's
the
components.
Okay.
Right? But as Evan said, the very best thing to do is to rotate your frame so that you've only got to have one of those.
Okay.
Yeah.
Suggested that we take the field from the proton and then use the rest of the information to put it in the frame of the electron.
Yes.
It's also viable if we do it the other way around.
Oh, yeah. Same thing.
So if we start from the frame of the electron and shift it.
Yeah, I'm only looking for the magnitude, so don't worry about which one's traveling.
Right. But the process is the same.
Process is the same.
It's like the portion, the difference.
Like momentum.
The constant.
Yeah.
That's probably good enough.